before we dive into the rest of the talk, let's do a very, very small recap. So we have seen, what have we seen? We have seen like these types. We have seen type classes. So what is a type class exactly? If you would have to explain this to somebody who knows Java, what would you say?
It's an interface.
Exactly, it's like an interface. Cool. And then we have seen different kind of types. So we have seen bool, it has true and false, and so we also have looked into lists. And so what are the two constructors for list?
So empty constructor and the constructor that constructs its
Yeah, so the cons operator. So, okay, cool. And so let's continue and look at some, we also saw currying. What was that again?
Say again?
Currying?
Oh yeah, just to make a new function by passing in fewer arguments.
Yeah.
I have a question actually about that. But can you do something like partially apply, but only on the third argument, for example? Not the
Yeah, if you want to do that, you can actually, you have operators that can switch the arguments.
Oh, okay.
But then you need to have like this swap operator. Mm-hmm. And then you can say like, I'm going to first swap the arguments a bit and then use. Sometimes it's necessary because you have two APIs and they don't really match up, and then you use these kind of operators. Okay, so there are a lot of list operators, and I'm just going to go through some of them, and I'm just going to tell you later on when we are implementing Snake, there's going to be some they are going to be useful, and so, but of course I don't expect you to like understand and remember all these ones once you've seen them. But for example, there is take and drop. Take is a function. It takes a number and then a list, and it takes in this case the first three of the list. So 3, 5, 4, 3, 2, 1. It's going to give you 5, 4, 3. And then drop. It's going to drop the first elements of a list. You can also take the minimum element, the maximum. You can also just take the sum of a whole list. So just going to give you the product and so on. And then you can also use element of a list. And so this back quotes, they indicate to Haskell that you are going to use, instead of writing the function in front, you are going to use it in between of the arguments. So you're asking whether 4 is an element of the list 3, 4, 5, 6. And of course, it's going to say true. And if you ask, is 10 an element of the list 3, 4, 5, 6, it's going to give you back false. Okay? There are a lot more list operators, but one is particularly interesting if you have never seen this kind of operator. It's called map. And so let's read first what the type of map is. Well, it's a function, and it's going to take another function as argument that transforms A's to B's. And it's going to, a second argument, it's going to expect a list of A's, and it's going to give you back a list of B's, right? And so here, some of the things that we have been seeing before are coming together, because here we are applying map to function where we have used currying. Yeah, so the plus function, we partially apply it to the number 1. We get a new function that whatever number that we give it to is going to increment that by 1. And then give it the list 1, 2, 3, 4, 5, and we are going to get a list 2, 3, 4, 5, 6, which is simply the list that we passed in where we have applied this function to every element of the list. Yeah? And so what's important to see is, you cannot really see it here, but it's not going to change this list. Right? It's going to make a new list. It's going to give you a new list where it has applied this function to every element of the list. So is this understandable for everybody? Then there are also ranges. This is, I don't think that we are going to use it in Snake, but it's something very handy. So you can, for example, say like, well, give me all the numbers from 1 till 10. And so you just write a list. You define the first element, then you write 2 dots, and then the nth element, and you get all the elements. You get a new list which has all the elements from 1 to 10. Yeah, you can also make an infinite list. It's very weird, but you can just write 1 and then dot dot. Yeah? And then you can take from that infinite list the first 10 elements. Yeah? And then it's going to happily give you back the first 10 elements. And you can also do this with characters. So this is one for all the for the alphabet. And then if you just write 1 dot dot, yeah, it's going to make a best effort of giving you all the numbers. And of course, this easily falls off your slide. But it's I'm not going to say too much about this at this point. But to give you an intuition, if you the order of evaluation in Haskell needs to be that that you are basically not computing the arguments when you are giving it to a function. Yeah? And you can clearly see that here because this is an infinite list. Yeah? And so instead, it's only being evaluated when it's strictly necessary to compute it. And so this is like this lazy evaluation, and you see it here, because you can just take the first 10 elements of an infinite list. So instead of in a call by value language, yeah, what happens is when you call a function, it's first going to evaluate the arguments completely. Yeah? In Haskell, you are going to evaluate the arguments at the moment that you really need it. And when do you need it? Well, actually at the point that you are printing it here. And so instead of here saying like, let's compute this infinite list, which is impossible, it's basically going to say like, well, I'm a list and I start with 1. And if you need the rest of me, I will compute it when you need it. That's kind of how you can think about it. And so when you apply take 10, it's just going to take the first element. And then it's going to say, well, give me the second element. And then it's going to say, OK, here is your second element. Give you a third and so on, till you have the first 10, and then you return. And so there is much more to say about this, but at this point, I think this is enough, just to give you an intuition about what this lazy evaluation is about. The list comprehensions, well, I'm going to skip them here, actually. OK, so I actually think this is like the last theory before we are going to jump over to actually implementing Snake. But it's an important concept. So the idea, the thing that I want to sketch is that you can actually keep track of state without doing assignment. Yeah? And so this is very crucial in Haskell because you don't have assignment. And of course, in a game or whatever you are doing, you want to somehow keep track of the state. Yeah, you want to know where your snake is, you want to move your snake, and so on. And so you somehow need to deal with that. And so let's say that you make a basket, and you want to keep track of the amount of bananas. Yeah? So you could make a pure function. And so what it basically does, if you have an empty basket, yeah, it's going to give you a new basket. Yeah? It might be confusing, but this basket is new, and it has a banana inside. Yeah? And whenever you give the add function an empty basket for the same input, it's always going to produce the same output, namely a new basket with 1 banana inside. Okay? If you give it a basket with 1 banana inside. It's going to create a new basket and it's going to put 2 bananas inside. Yeah, I think the important thing to note here is that it's actually a new basket that you're making, and here you can actually kind of take a reference to the previous banana. Okay. Okay. And so if we want to keep track, let's say, of a set of variables or a group of baskets, then we can also do that. So we can, if we have a group of baskets and we want to set, so of course this is the analogy of having some variables, and we want to set the first variable to this banana. So what we are going to make is we are going to make a new list of baskets, and we are going to put a banana in the first basket. And then the same thing with if we pass 2, we're going to make a new list of baskets, and we're going to put a banana here. Yeah. So we can make basically a list of baskets, and we call this state A. And so this A, it's a type variable. And that means that we can put different kind of types in our basket. Yeah? And so it has 2 constructors. Let's start with the empty state. That's basically the end of the list. And then we can put a variable, and it's going to keep track what its number is itself. So it's a variable. It has so instead of having a name, it basically has a number, and it's going to have a certain value A, the thing that you put in the basket. And then there's going to be, just like in a normal list, the rest of the state, right? Is everybody following with this definition?
What's the int for?
Well, the int is actually, maybe it could have been better if I put a list of cars there. So that's the name of the variable. That's representing the name of the variable. And so instead of having names in this model, variables have numbers. You can kind of look at it as addresses in the memory. No?
So why the double A? Like, I don't understand why there is a name outside the state and inside as well.
So the first A is indicating that it's a variable which has a certain address, let's say, and the value is this must be of the type A, yeah, and then it has the rest of the state, yeah, and we are not allowing to use any other. We are making a baskets of bananas or of integers or of list of strings and so on, yeah. Yeah, we can extend it. Yes.
It's like a list, right?
Yeah, it's exactly like a list.
Can
Yep.
you have others, like other states in states adding into? Because of this state A inside, can it have like baskets in baskets? And so
Yes, I'm not sure that you are referring to this, but you could put state. Yes, that could be possible. Yeah. And then there is this deriving, and so we have deriving, show, and equal. And so show, it's basically to make that when you use actually want to have a string representation of a state, that it's going to make a best effort to have a string readable version of your state. And equal means that it's going to basically generate an instance of the equal type class so that you can compare states with each other. And this deriving actually tells Haskell, do this for me. Yeah? And most of the time you can just use this deriving, and otherwise if it could be that it can say, it can tell you, sorry, I cannot derive this automatically for you. Yeah? Okay. Okay, so to set something, well, we take a state of A's. Yeah? We take a certain address, and we want to have a new value A for that address. Yeah? And then we get a new state. Yeah? So just imagine that we want to set something, but it doesn't on a certain address, and we want to give it a certain value, but we are doing this on the empty state. Yeah, what do we need to do? Well, we just create a new variable on this address with this state, and then the closing thing is the empty state. Yeah, and so we basically just add, well, this address has this value at this point. Everybody's following? So then we use pattern matching, and so if it's not the empty state, it needs to be like this variable with a certain address, with a certain value, and the rest of our state. Yeah. And we want to put we want to set the address v prime on a certain value x prime, and then we use something that we haven't seen yet. We use these guards. Yeah? And so what this guard says, well, use this branch in case that this predicate is true. So in case that the v, yeah, the address of this variable equals the address that we want to set, yeah, what do you do? Well, you create a new variable with on the same address with the new value. Yeah? So you kind of changed the variable at that address, and then you pass in the rest of the state. Yeah? Otherwise, it means that we want to set a certain variable on a certain address which is not the one in front of our state. So what we do is we basically leave this one untouched. Yeah? So we just put the same one here, but we are going to set in the rest of our state. Is everybody following with this last part? So we are going to set in the rest of this. Yeah.
So the int is like a key.
Yeah, a key or a key value or an address or. Yeah.
I was gonna say if we were to put the string, I think the example would be much clearer there.
Yeah.
Everyone is set on that string as a version. This is what I was thinking at the beginning. But it's variable 1, variable 2, variable 3. There's like different slots.
Yeah.
So, okay.
And so getting certain state out is very similar. This is a bit dirty because what I'm saying is like when you get something from the empty state, I just return 0. Yeah, in this case, and it's specialized for ints. Yeah. A better way would be to use maybe, but the only point I want to make here is that you can actually create state. You can set things, you can get things, and you can, but the point is that then you have to carry around this state. So, and then you get from a variable at a certain key. Well, if the key is exactly the same, then you get x, and otherwise you try to get that key from the rest of your state. Yeah? And so all this to get to this point where where we have a function, it takes a certain state, it takes a new value, and it returns the new state. Yeah, and so that's really the big pattern that I want to show. So you have a function, it takes like your state, and then does some stuff, and it returns you the new state. Yeah, and the whole point is that all this is purely functional. Yeah? It gets the initial state, it does something, and depending on, it's always going to return you the same return state if the input state is exactly the same. Yeah? So increment on a certain state a new value, well, we just call set as and on what we set it, well, we take the old one, which we get from the state at position 1, and then we just add it with 1. Let's see. I think I had this snake. Yeah. Okay. Increment 1. Wait. Ah, yeah, of course. Sorry. Yeah. So if you call increment 1 and you give it the empty state up on position 1, what is it going to give you? Well, it's going to give you a variable. At key 1, it has value 1, and the rest of the state is the empty state, right? And so if we then again say like increment 1 on this state with the same one, it's going to give you now, well, variable 1 now has value 2. Yeah.
How will it display if we have several different keys, like several different?
Okay, let's do this. So we just saw this one. So we can do increment 1 on the same state. So variable 1 has value 2 now, and the rest is the empty state. So if we now set variable 2, and we increment it with 1, so the initial value is always 0. So what is it going to, who has the cube? You can pass it on. So what is the result now going to be?
So now the variable with address 1 will still have the value 2.
Yes.
And the variable of address 2 will have value 1, and the rest will be empty state.
Yeah, very good. Ooh.
It's writing the position to the amount.
Ah.
Increment 1 doesn't really read the keys.
See, old x plus x,
What's
which
that?
should be x and then old x plus 1.
Wait, where? Can you tell me?
Where it says set s1, old x plus x, which would be set s x, old x plus 1.
926.
926.
926.
Always set to the first position.
Oh yeah, that should be.
It should be set s x, and then the old x plus 1.
Yeah. But wait, what is this one still? You take the state S at position X, right? Yeah. It's like this. Yeah, and then you get this. Good. So I should really adapt these slides. Let me change this quickly.
Increment by 1. Increment by 1.
Yeah, I think I actually think that I kind of explained it wrong because it was like increment the key 1, but I kind of explained it wrong. But this one is actually better, of course, to explain things. Sorry. So, but is everybody following? I think so, because the variable was right, and so okay. Questions at this point? So the whole point is that if you in Snake we are going to have some kind of state, and we are going to produce a new state. That's the whole point that we are going to do. So in order to create snake, we are going to make use of gloss, and so it's a really nice library. And here you have all the code that you need in order to display a window and draw a circle on it. Okay, so let's look into detail. Display, the first thing that it gets is a certain display, and in this case it's like in window, it's a nice window, it has size 200 on 200, and you put it at position 1010. And so then you give it a background color, and in this case it's white. And then you make a certain picture, and pictures are the elements which are being drawn. And so circle 80, it's basically going to make a circle around the origin. And so the origin in gloss is actually the middle point in your screen. Yeah? And so it's going to draw the circle around this origin. Yeah? Also, if you draw a rectangle, it's going to draw the rectangle around the origin. Okay, so that's one thing. So that's the coordinate system. So the point 0, 0 is in the middle of your screen. The y-axis goes up, and the x-axis goes to the right. That's important to know where to draw things. And so what we are going to use is a function simulate. And so it again gets like this this display, which is the window. Then it has a certain background color. Then it's taking a number, which are this amount of simulation steps to take for each second of real time. So that's like your frame rate, actually. And then it's getting like the initial model. And then it takes a function which takes a certain model and converts it into a picture. And so this model, it's like going to be the state of your game. And then you get a function which makes like one iteration. So it gets like a viewport, which is not so important, but it gets like the time and the previous model that you have had. And it's going to create a new model. Yeah. So given the current time and your previous model, you have to make a function which makes the next state of your game. So this model, that's basically like the state of your game. Okay, so let's look at a small example. So in this case, we are making a new in window, which is the same as before. It's like just a circle. We have the white background. We take 60 frames per second. And then our initial model, just to keep things very simple, it's simply a float 0.0. Yeah? And then we have a function which converts this model into a picture. And that's called draw picture. And so here we see draw picture. What does it do? Well, it takes the model and it's going to create a picture. And so in our case, we are simply going to make a red circle of a certain size. Yeah? And here we do some mathematics in order to, we are going to take modulo 200, and so that means that we are going to make the circle go big and then small and then big and so on. An update model, it's simply going to take the time, multiply it by 90, and it's going to add the previous size to it. So this is the time that we get. Yeah? And so we are just going to use this time in order to make a circle which is going to become bigger and smaller. So I think I have this as well. Let's see.
It's going to get smaller gradually. It's going to drop into being very small again.
Yeah. Is this cool? Nah. let me just take it from the slide. That's not going to work. Well, I'm going to let you first start with implementing it yourself. Okay, so for Snake, we are going to use the same idea of having this world and then making a new world and so on. And so the first thing that we need to do is look at which data are we going to keep for making Snake. And so one of the things you might think is like, we need like a big grid and so on, but actually you don't really need that. The only thing that you need is you need to have the snake and the coordinates of where your snake is and the size of the grid, and that's enough data to keep. And so we're also going to need to change the snake. We are going to need to make where the snake is going to. And so for that, we need a certain direction. And so in this case, we are just going to take 2 ints, and we are going to keep track of in which direction that we need to go. And so if we want to go up 1, we're going to do 0 minus 1. And if we want to go to the right, 1, 0, and so on. And so by using this pair, changing direction is going to become really easy, because you basically need to take the old value and just add where you are going to. Yeah. Okay. And so if we have these coordinates and then we have a certain snake, then 0, 0 for our snake coordinate is going to be the top left one. Yeah. And so if we go to the right, we are at 1, 0, and so on. And so if we have this snake representation, we can have this this representation, because a snake, it's a list of coordinates. Yeah? And so I didn't explain this, but in Haskell, you can also make what is called type synonyms. Yeah? And so basically what we are saying here, well, whenever you see coordinate, or what I mean is a pair of ints. Yeah? And then whenever you see type snake, what I mean is a list of coordinates. And so in this case, we can represent the snake like this. And then, of course, we need to know whether the player is alive or dead. So we need some data to type status. And it has 2 constructors, alive and dead. And we derive show and equal so that we can print this and compare the status. Okay, and then an apple, what we do here is, well, an apple is just a coordinate where you need to draw the apple, and it also keeps track of a random generator, because when you need to create a new apple, you basically are going to need to create a new random number. And so this std_gen, it's something here. So you can make a new generator. It takes an int and it creates you a new generator. And then, so if you ask like, what is this exactly? Well, the point is that it's an instance of random gen. Yeah. And so in random gen, you can call random with which basically takes like this generator, and it creates you a new number a together with a new random generator. Yeah. So when you call random on a generator, it's going to give you the new number that you need and a new generator which will produce a new random number. Yeah, so it's a pseudo-random generator. Don't use this in cryptography because it's not going to be very secure. And so this leads us to representing the whole world of our snake. So, well, we define a new type world. It has one constructor, world, which consists of a snake, the direction in which the snake is going, the time that we have been executing the program, the status of the program, and the apple. Yeah, and that's basically all that we need in order to start implementing Snake. Okay, so it's 35. We can actually start. So the way that that we are going to do this is first of all, I'm going to put a zip on Discord, which is like the skeleton code. Maybe I can still show you how it should look like in the end. So this is what you will end up with if you implement everything. And so if you just run into the site, it's going to stop, and then when you press enter, you can start a new game. Okay. So there is a platform called Dodona, in which I put 9 exercises, and if you solve these 9 exercises with some additional ones in the skeleton code, you end up with a working Snake game. So how do you log in? I'm going to pause on these logins, and so it's not super long, but it's a bit longer. So I recommend that you go to this URL and then simply scan the QR code. So they're all different. Yeah, they're all different QR codes, and they have a name. So if you prefer to have a certain name, you can go through this. They're all fake names, of course, but you can just go there. And so if you go there, you will get to a page. I don't have internet, of course. So why not? A 542. Okay, so if you, well, let me put it a little bit bigger. What?
Which website?
Well, the QR code you need. So, well, let me just show the website first, and then so what you will see is in your case it will be still not that you haven't handed in yet, and then you go to the first exercise. I recommend you to follow them in order. And so the first exercise is basically saying, like, when you have a coordinate, you need to know whether it's within the field. And so we define the field to have width 64 and height 64. And so the first exercise simply consists of taking this, finishing this inbox, and usually there will be undefined here. And so let's say that we that I always say false. So it's probably going to crash now, because for some reason the first time that you run the evaluator, when it has not been running, it takes too long. But let's see, it's going to give a timeout, and then afterward it works fine. So because I now did this, you should probably not get this timeout now. It has something to do with the caches, because there are like a number of there are 3 servers running this, and once it's in the cache, it works fine. And so in this case, I always put false, yeah, and so it basically says like, no, your solution is not correct because I could falsify it. What I had to give in to falsify it was 0, 0, and so it's 0, 0. It should be true, and in our case it was false, so it's not correct. Okay.
What institution do we need to use for this finding?
So this is let's all log into this Dodona first. So
So when I go to the login page, it shows me a list of many categories of institutions. That's the.
no, you should use the QR code.
Okay.
And if you log in with the QR code, can somebody give me one? Where is the?
Here, on the.
Yeah.
On the left.
So this is what you should see. If you're seeing something else, there's something going wrong. And so on the top right, you can change the language. So because I see that apparently it's in Dutch here, so you can change it in English, and you can press then on monadic party, which should show you all the exercises like this. It's not working for you. Maybe use this one then.
No, I don't have a QR code scanner in my computer.
So that's why I'm telling you that you can use this website. So in this website, you can scan the QR. Is this so? Who logged in successfully? Okay, so almost everybody.
So these are fake names, yeah?
Yeah, they are fake names. Because I didn't know the participants beforehand, and I didn't know who was going to follow the. They are just fake names. Okay. Okay. Okay, so what I'm going to upload very shortly is this file. Well, maybe just wait 1 minute now. Yeah, let me explain. So I'm going to upload this file, which has like all the skeleton code. Yeah, because on the website you're not going to have all the. And so I also wrote quite some documentation, and it would be nice if you read this. Yeah, so just open the skeleton code and then read till the point that you encounter an exercise. So the first exercise, and they all have like a difficulty level, which should give you an indication how difficult it could be. I'm not 100% convinced that this it's going to be different for everybody else, for everybody. So the very first one I didn't put in Dodona because it's quite easy. But that's basically indicating the directions for going left, right, up, and so on. Yeah. If you don't remember exactly how this worked, I'm going to now put on Discord the slides and this skeleton code. Yeah. So this is Discord, and that's going to be snake.zip upload. That's that. So you should be able to find it there, and then the slides, they are here. No, I cannot upload. So how big is it? So it's 9.8. So maybe I can still optimize this file, reduce file size. So that's a bit of a pity. The resolution is not going to be that high because I cannot upload files bigger than 8 megabyte apparently, but it's still very readable, I think. If something would be unreadable on the PDF, just tell me and I will try to fix that. Okay. There are four minutes left, so I think if now you have logged in, you have the skeleton code, and when you run the skeleton code, it's going to give you an undefined error, which is normal because I put at various places where you need to fill in the code undefined, right? Yeah, so that's in Cabal. So let me. So if you do Cabal, so you need gloss and random, and so what you can do is if Cabal install, which will do that, but of course I already did this. And then it's going to make the things. And then you can use Cabal run to execute it. Which is perfectly fine. It's going to tell you, well, I found an undefined on line 264, which is, yeah, of course, because you need to fill in the exercises.